Welcome, everyone, to another Explainer. Today, we're going to be exploring one of the most elegant balancing acts in the entire natural world, and that's biochemical stability. Now, whether you're already deeply immersed in the life sciences, or maybe you're prepping for a major exam like the CSIR-NET, understanding exactly how life maintains its internal harmony is just absolutely fundamental. We're looking at nature's equilibrium, the biochemistry of buffers.
Okay, let's dive right into this. Here is our roadmap for today. We'll start with the fundamental chemistry in the concept of buffers, then look at the mechanisms of equilibrium. From there, we'll decode the math with the Henderson-Hasselbalch equation before scaling up to those complex physiological ecosystems in biological buffer systems. And finally, we'll zoom right in on the life-saving dynamics of blood and bicarbonate. All right, let's kick things off with Section 1, the concept of buffers. So, what exactly creates these ultimate stabilizers in the natural world? Well, a buffer system is basically life's chemical shock absorber. By definition, it's a solution containing a weak acid and its conjugate base that actively resists changes in pH when a small amount of acid or base gets added. It's kind of like a dense forest canopy, right? It protects the delicate forest floor from a sudden torrential downpour by absorbing the shock, keeping the whole environment down below perfectly stable.
But, even nature's best shock absorbers have their absolute boundaries. A buffer system can really only resist pH change exactly one pH unit above and below its specific pKa. Let's look at the acetic acid and acetate buffer as an example. Its pKa is exactly 4.76. And because of that strict mathematical boundary, its operational limit, the actual zone where it can functionally protect the solution, is strictly from a pH of 3.76 to 5.76. Once you step outside that narrow window, the chemical shock absorber just completely breaks down.
So, how does this actually work down on the molecular level? Let's move to Section 2, Mechanisms of Equilibrium.
Let's observe the microscopic battle that happens when an invader shows up. Think of the weak acid, in this case acetic acid, as this massive reservoir of protons. In step 1, when an invader, like a strong base containing OH- enters the system, the acetic acid essentially opens the floodgates. It releases H+ to neutralize that OH- right into harmless water, adapting the equilibrium to maintain the water constant Kw. On the flip side, in step 2, if an acid is added, the conjugate base, the acetate ion, steps right up. It accepts those invading H+ protons to form more acetic acid, completely restoring the balance. It's this constant, brilliant dance of give and take. We've seen the narrative behind this dance, but chemistry is, of course, always governed by strict rules. So let's transition to Section 3, the Henderson-Hasselbalch equation. Now, what's really interesting here is how this one elegant, simple mathematical blueprint directly describes the complex shape of a titration curve. It simply states that pH equals the pKa plus the logarithm of the concentration of the conjugate base divided by the concentration of the weak acid. Honestly, if you're deep into life science studies, committing this specific relationship to memory is absolutely non-negotiable. It is literally the master key to unlocking how varying concentrations directly manipulate the pH of any given solution. And right here is where perfect equilibrium happens. When the molar concentrations of the weak acid and its conjugate base are exactly equal, the math does something beautiful. The ratio becomes 1, the log of 1 is 0, and so the pH of the solution becomes numerically equal to the pKa of the acid. That right there is the exact midpoint of a titration curve. It represents the state where the buffer system is at its absolute unyielding peak performance. Which leads us to a really fascinating question. How do these strict chemical rules govern the incredibly delicate ecosystems inside ourselves? I mean, we know what happens in a test tube, but how does this apply to the biological symphony happening inside you and me right this very second?
Well, let's find out in Section 4, biological buffer systems.
You see, biological processes are unbelievably sensitive to pH. Even the tiniest shift can drastically alter biochemical reaction rates. So, to survive, life requires these highly specific systems. And this brilliantly illustrates the three main biological ecosystems keeping us alive. First up is the phosphate buffer system, operating heavily in the cytoplasm of your cells. With a pKa of 6.86, it's perfectly tuned to resist pH changes in that critical 5.9 to 7.9 range. Then we have the bicarbonate buffer system, which acts as the primary guardian of your blood plasma. And finally, the amino acids buffer system. Certain amino acids have ionizable side chains, like histidine, for example, which has a pKa of 6.0, giving it excellent buffering activity right at physiological pH.
These three systems are literally the invisible guardians of your cellular integrity. For our final segment, let's zoom in on what is arguably the most critical buffer system for human survival. Section 5, blood and bicarbonate.
Okay, so your tissues are constantly metabolizing, right? And their main exhaust is carbon dioxide. Well, the bicarbonate system provides the essential means for removing this CO2. It's an amazing chain reaction. The concentration of carbonic acid, that's H2CO3, depends entirely on the concentration of dissolved CO2 in your blood. And that dissolved CO2, it relies completely on the partial pressure of CO2 in the gas phase within your lungs. It's this beautiful bridge between the actual air you breathe and the chemistry happening in your veins.
So the crucial point here is this highly specific ratio, 20:1, 20/1. The pH of your blood absolutely must be maintained at exactly 7.4. And the only way the human body achieves this perfectly balanced, life-sustaining pH is when the buffer ratio of bicarbonate to carbonic acid becomes exactly 20:1. If this simple chemical ratio shifts too far in either direction, life ceases. It's really that serious. Because this ratio is so incredibly vital, your body fiercely protects it using two totally distinct physiological pathways. When bicarbonate neutralizes an acid or a base, it threatens to throw off that delicate 20:1 balance. To compensate, your lungs can perform respiratory removal, basically rapid firing to exhale CO2 gas and thereby reduce carbonic acid. At the exact same time, your kidneys can step in with urinary removal, systematically filtering out bicarbonate ions. It's this continuous, incredible collaboration between your respiratory and renal systems, all dedicated to maintaining that one precise chemical fraction. It really puts things into perspective, doesn't it? If a simple chemical ratio is the fine line between life and death, how effectively is your biological ecosystem buffering you right now? Every single breath you take, every metabolic reaction happening in your cells relies entirely on this silent, perfect equilibrium to keep you alive and functioning. It really is an invisible masterpiece of nature's design. Thanks so much for joining me on this explainer. Keep wondering, keep learning, and I'll catch you next time.